In Lesson 3.1, we will be discussing exponential functions. In Video 3.1.6, our learning target is for students to be able to solve problems involving exponential growth and decay. Before we get to solving problems with exponential growth or decay, there are a few formulas that we need to discuss. If an initial quantity, n0, anything with a subscript or little zero next to it is called an initial amount or initial quantity. If that initial quantity grows or decays at an exponential rate r or k as a decimal, then the final amount n after time t is given by the following formulas. The formula we'll use for exponential growth or decay, if r is the growth rate or the decay rate, okay, growth implies that r is going to be greater than 0. The decay rate implies that r is less than 0. So if you have a negative r value, the quantity is decreasing or decaying. If r is greater than 0, then you're having the initial amount is going to be growing or increasing. Now here's the deal. N in this formula represents the amount after time t, and 0 is or n sub 0 is your initial amount. R again is your growth or decay rate, depending on whether or not the object or whatever you're looking at is growing. That will be positive. If R is negative, then the object or the substance you're working with is decaying or decreasing. T is time in whatever unit of time that they measure or give you. For continuous exponential growth or decay, that looks similar to our continuously compounded interest formula. N is the amount of the substance when N0 is your initial amount. E is still 2.71. K is your continuous growth rate or continuous decay rate. Again, if K is greater than 0, the substance is growing. If K is less than 0, your substance would be decreasing. And T is time. So N would be your amount of whatever you're measuring, if it's bacterial growth or population growth. N is going to be your population or your substance left after time t. So just to review that, over here, N0 is your initial amount, just like our principal in those compound interest formulas. R is your rate, and that again has to be a decimal. And T is time in whatever unit they give you. Same thing happens over here, just K is your rate rather than R. And so they just use a separate variable to distinguish between a growth rate and a decay rate versus continuous growth rate and continuous decay rate. And K also has to be a decimal. In example 6, we will be modeling growth or decay, exponential growth or decay. This situation is dealing with population. A state's population is declining or decreasing or decaying at a rate of 2.6% annually. Remember that word annually, it means yearly. The state currently has a population of approximately 11 million people. If the population continues to decline or decrease or decay at this rate, predict the population of the state in 15 and in 30 years. Okay, our rate of decline here is not continuous. It's annually, so we're going to use the first formula that we discussed on the last slide, where we have N equals initial amount times 1 plus our rate, raised to the power of t. Now, here's what happens. We want to know, we're going to have two different problems here that we're going to solve. We're going to find the amount n, population, after 15 years and after 30 years. If our population is declining or decreasing at a rate of 2.6% annually. Well, they gave us the initial population, which was 11 million. I'm not going to write out 11 with 6 zeros after it. I'm just going to use 11 as my initial amount. And then I would have 1 minus 0.026, 2.6% as a decimal. If I move the decimal place over 2 places to the left, I get 0.026. The reason why I'm subtracting 2.6 is because our R value has to be negative because the population is declining. And for time, I'm going to plug in 15 years. So the number of people in this state is going to be 11 million times, if I take away 2.6%, that's going to be 1 minus 0.026, which gives me 0.974 raised to the 15th. So if we're looking at this, basically what we're saying is that each year the state is only retaining or keeping 97.4% of its current population. So if I work this out on my calculator, I'm going to take 0.974, raise that to the 15th power, and then multiply by 11. And I'm going to get 7.41 million people. So this state can expect there to be 7.41 million people after 15 years. To calculate the population after 30 years, we will use the same formula using 11 million people as our initial population. We are still declining or decaying at a rate of 2.6% annually. 2.6% is 0.026 as a decimal. And we'll raise that to the 30th power because we want to know the population after 30 years, so t is 30. So if I simplify following the order of operations, I'm going to subtract 1 minus 0.026, which we already should know is 97.4%. So each year we're only retaining 97.4% or keeping 97.4% of our current population. And over the course of 30 years, 0.974 to the 30th power times 11 will give us 4.99 million. So we have approximately 5 million people after 30 years. When we started out with an initial population of 11 million, we are declining at 2.6% annually or yearly. And so after 30 years, that gives us approximately 5 million people. In real world example 6, we are going to model using exponential growth or decay. We are using a population example again. This time a state's population is declining at a rate of 2.6% continuously. The state currently has a population of approximately 11 million. And if the population continues to decline at this rate, we can predict what the population of the state is in 15 and in 30 years. Now, if we're going to use continuous decay or continuous growth, but in this example, since the population is declining, we are using a decay model. Same equation either way, growth or decay. It's just going to affect what our k value is. So that formula that we had on the first slide was n equals n sub 0 e raised to the k times t, where n0 is your initial population, so I'll substitute 11 for our initial population. Remember, e is that irrational number, approximately 2.71. K is going to be a negative 0.026 because k is negative because our population is declining. And t for time, in this case we're going to use 15 years. Initially here we want to calculate the population after both 15 and 30 years. So calculating our population after 15 years, I'm going to type in 11. This E can be found by pressing second ln on your calculator. That ln button is like just to the left of the 4 on your calculator. So if I press second ln, that gives me that E. And raised to the negative 0.026 times 15 is going to give me 7.45 if I round to the nearest hundredth. And that is in millions of people. Sorry, million. So we have 7.45 million people left after 15 years. If our population is declining at 2.6% continuously. Now, on the next slide, I'm going to calculate what our population would be if that decay occurred over the course of 30 years. Since I rounded the 7.45, it was 7.447, I should really say that N is approximately 7.45 million, not exactly 7.45 million. If I wanted to write my answer out in millions, I would then take the 7.45 and multiply it by 1 million. And I would get 745,000, which is 7,450,000. That's the equivalent of 7.45 million people. So if we're going to calculate the population after 30 years using the same formula, I would say 11 million people. E, still negative 0.026% as our decay rate. And time is going to be 30 this time rather than 15. So when I calculate this on my calculator, I'm going to say 11 times E raised to the negative 0.026 times 30. And I get an N value of 5.04 million people. So just over 5 million people would be left after 30 years if our decay occurred at a continuous rate of 2.6%. Now what I really should say, since I rounded the 5.04 and cut off some decimals, I should say approximately 5.04 million, or I can multiply the 5.04 times 1 million, or multiply it by 1 million, and get 505,040,000. In Real World Example 6, in Guided Practice, we will be discussing population again. The population of a town is increasing at a rate of 2% annually. Annually again means yearly. If the current population is 15,260 people, predict the population in 10 and in 20 years. You have 4 choices here, A, B, C, and D. I would like you to go ahead and calculate your response and then hit submit once you have decided on your response. In Real World Example 6, Part B, our population is going to increase at a rate of 2% continuously rather than annually. If the current population is 15,260 people, predict the population in 10 and in 20 years. You have 4 choices for responses here. I would like you to calculate your response and then choose either A, B, C, or D and press submit.